gentlemen, boys and girls, children of all ages, please welcome Professor Bassam Z. Shakhashiri.
Hello, everyone. Welcome to my lab. I'm very happy to have you here. Are you ready to learn? Yeah! Are you ready to have fun? Yeah! Well, you know we must do the experiments in a very safe way. That's why I put my goggles to protect my eyes from potential damage. Before I did that experiment, I also want you to see that we have a fire extinguisher ready to be used just in case something goes out of control. We're not planning on anything going out of control, but it's a safety measure that we are taking. Now, you notice that the balloon that I brought in had in it a gas lighter than air. That gas also exploded when I put the flame to it. Some gases burn and some other gases don't burn. But what we like to do in science whenever we do an experiment is repeat the experiment. And that's what we're going to do now. But instead of using this as a lighter, I'm going to use a gas called natural gas in this torch as the way by which I'm going to ignite the balloon. So we've got another green balloon. And what we're going to do is repeat the experiment in the dark. So here we go. Watch and see. Now with the lights up, with the lights up, you were able to see that experiment somewhat differently in the dark than it was with the lights on. Let's take a look at that last experiment in slow motion. So watch the monitor. There's the balloon. Oops, there's the flame actually, not just the balloon. And that is the replay in slow motion. Now that balloon had in it hydrogen gas. Let's move on and do an experiment with this yellow balloon that has in it a gas lighter than air. So I'll put the torch to it. Whoops, what happened? Nothing. What do you mean nothing? The balloon popped, but there was no flame, right? That's because the gas in that balloon is helium. And helium is one of the gases that does not burn. Now we've learned so far that some gases burn and some gases don't burn. Some gases like hydrogen burn and release energy in the form of light, which is what we saw, but also release energy in the form of sound, which is what we heard. Before doing the rest of the experiments with the balloons, I'd like for each of us to obey the safety rules and regulations by protecting our ears from potential damage, by taking the two fingers and putting them in our ears like this, so that we protect our ears from potential damage. I can't do that and do the experiment at the same time. So I have brought with me some earplugs. So I'm going to put the earplugs, and I'd like to ask you to protect your ears very, very carefully. If you can hear the sound of my voice, that means your ears are not well protected. I can't hear you, but I see you smiling. That means you heard what I said. So please protect your ears as we go to the next set of balloons and put the torch to this one. That balloon had in it a mixture of hydrogen and oxygen. In other words, there was much more oxygen available for the hydrogen to combine with in that very, very loud explosion. Let's repeat that last experiment, but let's repeat it in the dark. So first, let's put our earplugs in. You protect your ears very well. We'll turn the lights down and repeat the experiment in the dark. We learn more about experiments that release energy in the form of light if we do them in the dark. Let's take a look at this last experiment in slow motion. Watch the monitor, and you will see the light coming up to there's the torch coming up to the balloon. You won't hear any sound, the flame will hit the balloon, and there, very fast reaction, very fast explosion. Well, throughout the years that I have had the privilege of presenting this very special program to you and to others on public television, I've had also the privilege of working with some very talented people. And I would like for you now to welcome one of my colleagues who has been with me for almost 25 years. That's Dr. Rodney Schreiner. Rod? What do we have here?
Well, because this is your 25th anniversary, I thought I'd bring out some things to improve the celebration.
All right.
And nothing improves the celebration like ice cream.
I agree.
So I brought the ingredients for ice cream.
Okay.
Cream, strawberry,
Yes.
preserves,
Ooh.
vanilla,
Whoa.
sugar,
Okay.
eggs,
Eggs.
and
And a bowl.
a bowl.
All right. And you want me to help with this?
Yes.
Or- okay. What shall I do?
You can open the cream and put it in the bowl.
Open the cream and put it in the bowl. All right. It says, thank you for selecting. Oh, I won't read the brand here. Just to open. All right. I open this and put it
pour
in the
it all
bowl. All right. I can do that. I see you have your goggles on. So
Well,
that's good.
Yes, you never know. Making ice cream might be hazardous.
Hey, that's a nifty shirt. Can I get one like that?
Maybe.
Maybe. Oh, all right.
But this
Okay.
one's mine. You can't have it.
Okay, that's yours. What do I do next?
Add the half and half.
Half and
I'll
half.
put the sugar in.
Okay. Does it make any difference how well you mix this or what?
Well, I need to stir it to dissolve the sugar.
All right. This is rich ice cream, it sounds.
Well,
looks
nothing
good.
but the best for your
Right.
25th.
What do I do next?
Well, we're going to need some eggs in here
Eggs.
too.
I
so,
got the eggs.
So break the eggs and
Break the eggs. Okay.
mix them together.
Okay. Mix them together. Do I need an instrument to mix them together? Oh, yes,
Yes.
you got it right here. Okay, fine, I'll do that. What's this thing called?
A whisk.
A whisk. And just whisk it around a little bit, right? Okay. How much?
Not common laboratory apparatus.
All
I
right.
know.
Well,
Okay,
you know-
that looks good. Now you can
good.
pour the eggs into
Pour the
this
eggs in
mixture.
there.
And I'll take the whisk from you.
Take the whisk. You need the whisk, all right?
Yes. So now we have the main ingredients for ice cream, the basic mixture.
Yes.
Now we need to flavor it.
All right.
So I've brought the vanilla flavoring.
Yes. How much should I put? Just dump it in?
No, don't. This is a laboratory. We have to measure.
Measure, and how much should I measure? I have measuring devices here.
1 tablespoon.
That's this big one.
That's the big one.
All right.
I know you're used to metric units. That's
Yes.
15 milliliters.
15 milliliters, all right? What's next?
And because this is a very special occasion, I want more than just vanilla ice cream. Let's add the strawberries to
Ah,
make
that's what the
strawberry ice
strawberry's
cream.
for. And you even brought a spoon. That's great. Now, is this going to be real ice cream? I mean, how are we going to do this? Or is it ready to be?
Well, I'm counting on you to have something very cold in your laboratory that we can use to freeze this.
Something very cold.
Yes.
I have lots of cold things. I have something really, really
You
cold.
usually do have cold
It's
things.
called liquid nitrogen. Will that do?
That's cold. That's
All right.
cold.
All right.
Oh,
I've got the liquid nitrogen right here. But this is really cold. It's minus 196 degrees Celsius.
well, that should do it.
That should do it?
should do it.
Okay.
So, combine the ice cream mix.
Yeah.
Get all these strawberries in here.
Strawberries are good. Yeah. Okay. Now what do I do?
Pour the liquid nitrogen
Pour
into
the liquid
pan.
nitrogen. That's going to really freeze it.
That's the idea.
Are you sure this is going to be edible?
Oh, absolutely. Nothing but the best ingredients.
All right.
Oh, it's getting stiff.
Getting stiff. Okay.
It's more than stiff. It's getting hard is what's happening. Ooh, it's
Oh, boy.
getting very hard.
Well, when
It's extremely hard.
it's very hard, but it's also cold, I bet you.
Minus 196, you said.
Right, Celsius, right. So
I don't think I'd want to eat it when it's quite that cold.
not this cold. So what should we do then?
I think I'll take it back and put it in the refrigerator and let it warm up.
But let it. But we will get it back, right?
Oh, yes.
Oh, okay.
We'll bring it back.
Well, thank you very much, Rod. Well, the next experiment that I'm going to do is with another cold substance. It's not as cold as liquid nitrogen. This substance is called dry ice. It's actually solid carbon dioxide. The temperature of this solid is minus 78 degrees Celsius. I will use the gloves to protect my hands from frostbite. Although these are garden variety gloves, they're not very well insulated. I will not squeeze this or hold it very tightly. Just pick it up and put a chunk of dry ice on the tabletop. Dry ice changes from being a solid to a gas directly. In other words, it doesn't melt. Substances that do that undergo a process we call sublimation. There is gas coming off now from the dry ice, but we can't see it. What I'm going to do next is an experiment with the dry ice to show that the sublimation is taking place, actually show a few other things too. So I'd like you to focus your attention on this part of the table here where I have in front of me some cylinders. These are cylinders that have different colored liquids in them. How many cylinders do I have? How many? 10. 10 cylinders. And as I said, they have different colored liquids in them. And I'm going to put chunks of dry ice in those cylinders in a very special way. And when I get done, you tell me what this special way is. So here we go. What's the special way that I'm doing? Did I put the dry ice in every cylinder? I put in every other cylinder. Lots of interesting things are happening. You see those bubbles? Those are gas bubbles. Those are carbon dioxide gas bubbles. The carbon dioxide dissolves in the water and forms carbonated water. We all know about carbonated water because we drink carbonated beverages. And carbonated beverages have in them carbonic acid. You also notice that something else very interesting is happening. Lots of things are happening that are interesting, right? There is what? A color change that's taking place, right? What I have here are some dyes that change color as a chemical reaction takes place. They indicate to us that a chemical reaction has taken place. They're called indicators. And the carbonic acid is combining with the different chemicals that are in there, and they each have their own characteristic colors depending on whether they're acids or bases. You also notice that coming off the top of those cylinders is something. What does this look like, that stuff that's coming up? It looks like foam, but it's not foam. What does it really look like? No, steam is invisible. You can't see steam. It looks like fog. You're right. And you know what fog is? Fog is condensed water vapor. The water vapor is condensing on the carbon dioxide that's coming out from the tubes, from the cylinders. And you notice that the fog is moving in a downward direction, telling us that carbon dioxide is heavier than air. So what I want to do next is an experiment with more dry ice, and I need some hot water. I don't have any hot water down here. Could someone please bring me some hot water? Please? Ah, thank you. Bucky? And welcome to my lab, Bucky. So happy to see you here. You are very, very kind to come to my special silver anniversary. I know you've been coming every year. You're one of the best students I've had in my class. You're a very, very good student. And I know you are because you have your eye protection. Bucky is wearing goggles. Yes, so do I, yes. And I know you learned that from me. That's very good, Bucky. I know you're getting ready for final exams, aren't you? Yes. I hope you are. I hope you are. I know this is a good, yes. You'll do well on the finals, especially if you study for them. Well, let me do the experiment, Bucky, that you brought me the hot boiling water for. This experiment I'll do in this empty dish pan. It's empty except for air. And what I'll do is I'll pour the water, the hot water, into the dishpan. You see anything coming off the top? Now remember, steam is invisible. That's not steam. It's condensed water vapor. You know, on a very cold day, when you blow your breath on your hand, don't tell me you see steam. You're seeing condensed water vapor. Well, here's the experiment, Bucky, that we're going to do here. We're going to take lots of dry ice, not just some dry ice, and pour it into this hot boiling water. You like that? This is how they make fog in the movies sometimes. They take hot boiling water and add dry ice to it. You notice once again that the fog is moving in a downward direction. That's because carbon dioxide is heavier than air. So, you like that experiment, Becky? Yes, I'm glad that you like it. I have a lot of other experiments that I think you will like, and I would like to ask you, I know you have to study for your finals, but can you stay for the rest of the show? Do you want Bucky to stay? All right, Bucky. I've got a special seat saved for you right over there. All right, Bucky. Make yourself comfortable and keep those goggles on. And what I have here is a big cylinder of helium, and what I'd like to do is repeat one of the most favorite demonstrations that I've been doing in the past 6 years for this lecture. So here we go.
Good evening, hockey fans.
And this is a physiological effect. Are we back? Which, among other things, makes people very dizzy if you inhale a lot of helium, because, of course, you're replacing the oxygen that is so very important to my life with helium. So I think we will do no more of that demonstration. I'm going to take a large can. I'm going to take this cafeteria tray too and put it right here. Take a large can that has an opening. It's empty except for air. And I'm going to put a little bit of water in it, like so. And then I'm going to heat the water. I'm going to try to boil the water by putting the can on top of this tripod, below which is a burner. I'll turn the gas jet on and strike a match and light it. What I want to do is allow enough time to pass so that the water boils. When the water boils, we're going to see something coming out of the opening. It's going to be the condensed water vapor that we will see. So we'll get that going. I also want to get something else going at this end of the table. I have a beaker that has a volume of 2 liters. In it is a sheet of copper that has been cut in the shape of a tree. And I'm going to add to that a clear and colorless liquid to cover the tree. We'll come back and take a look at this reaction to see if anything is happening as we move on to do other experiments. What I want to do then, as we're waiting for something to happen, is to ask you to focus your attention at these 2 large flasks that I have. The bottom flask is filled with water. It has a volume of 5 liters. And the top flask looks empty. It's actually not empty. It has in it a colorless gas. It's invisible. The name of the gas we have in here is called ammonia. Now this flask, it's filled with ammonia, which we cannot see, is connected to the bottom flask by a piece of glass tubing running through this 2-hole rubber stopper. And the other hole has in it this the bottom of a medicine dropper and this rubber bulb. The rubber bulb has some water in it. What I'm going to do is squeeze the bulb so I can squirt some water into the top flask and see if anything happens. That's why we do experiments. We mix things together to see if anything happens, and we try to be attentive about it. So here we go. I squeeze this. What you see happening here is the siphoning of the water from the bottom flask to the top flask. That happened because ammonia, the gas ammonia, dissolves in water. And the small amount of water I squeezed out of the rubber bulb here dissolved all the ammonia that was filling up the top flask and created a partial vacuum up there, causing the water to be siphoned from the bottom flask to the top flask. And we have an indicator in here to indicate to us that ammonia forms a basic solution when it dissolves in the water. So this is a kind of an interesting experiment that has to do with the effect of the solubility of a gas, and then the fact that the atmospheric pressure pushes on the water and causes the siphon to go up. All right, let's see if we can, in the next few moments, do some of the favorite experiments that I've done in previous programs. And I get a lot of mail about the experiments. I wish I could repeat all of them, but I'm going to just do a couple right now very quickly. The first one has to do with reaching into my wallet and seeing what I have in my wallet. Oops, I see that I have a dollar bill in my wallet. I'm going to take this dollar bill and put it in the flame. And did you see that? Was that too fast? Well, you know what we should do? What we always do is repeat the experiment. So I'll do it now more slowly. I'll take what looks like a dollar bill. It's not a real dollar bill. It's a phony dollar bill. It's a fake dollar bill. This dollar bill, this fake dollar bill, has been made of paper that has been especially treated so that when it burns, it doesn't leave any ash behind. So let's repeat the experiment now. Go to the flame, and as soon as it touches it, there, it disappears into thin air. Okay. I'm glad you like that one. Let me see what else you have. What else I have in my wallet. I have a $20 bill, and this is a real $20 bill. You suppose I can do the same thing as I did with that? No. Well, I'll tell you what. What I want to do is take this jar that has in it a clear and colorless liquid. What do you suppose this liquid is? What does it look like? It looks like water. So let's see. What happens when I take the $20 bill, I just soak it in this liquid. I have a pair of tongs here to help me fish it out. I'll soak it in and fish it out. You see it's dripping like any wet object would, or does. And I take this to the flame, and there's a $20 bill on fire. Or is it? You did see a flame, right? $20 bill is intact. So could this liquid be water? No. This liquid, I will tell you what this liquid is. This is a mixture of something we call rubbing alcohol and water. This is a 50% mixture. Rubbing alcohol you can get in the drugstore, and water you can get anywhere. And it's the alcohol that was burning. That flame that we saw was from the burning of the alcohol. And this experiment tells us that this alcohol burns at a temperature lower than the temperature at which the paper from which this $20 bill is made. Well, this is a good $20 bill. I'm going to put it back in my wallet before something else happens to it. I'll close this jar and move on to do another experiment that we've done before, and a lot of people like it. This experiment, let's see, I need to connect the hose to the gas jet so I can then light the burner and take a match, light the burner. There is a lit burner before us. And what I'm going to do is take out of this small squeeze bottle a powder and squeeze it into the flame. Isn't that neat? This powder is called lycopodium powder. It's a finely divided powder. It's dust, almost dust. And you know, sometimes we hear about explosions, dust explosions that happen in silos. That's because the corn or whatever else is being stored in the silo changes, some of it changes into dust, and it catches on fire and very, very rapidly, just like this one did. Okay, let's take a look at what's happening over here and see if we can see any condensed water vapor coming out. Can you see any condensed water vapor coming out? Let's make sure this is really going hot. You see some? There's some coming out, some evidence that this is going on. So what I want to do is use this cafeteria tray to put some ordinary ice in it. Just going to put some ordinary ice in here because I want to use this ordinary ice to cool the can. And to do that, I can't handle the cans with my bare hands because the can is very hot. So I'm put my gloves on again to protect my hands this time from heat, not from cold. And to do this experiment, I will take a rubber stopper and plug up the hole that's up there, all right? And what I will do is plug it up like so, lift it up, and put it on the ice, and we'll see what happens. The can got crushed. That's because the pressure inside the can got to be less than atmospheric pressure. And the question is, how did that happen? Well, you know what? You can do this very same experiment at home, but you don't need a big can like this. All you need is an empty soda can like this that you've emptied. You put a little bit of water in it, as I'll show you now. And you put it so that the water boils off. And what are we looking for? We're looking for evidence that the water has boiled. And what we're looking for is condensed water vapor coming out of there. So it takes a little while for that to happen. So we'll wait for that to happen. But we'll try to talk about why this happened. The pressure of the atmosphere caused the can to collapse, to be crushed. And this happened when after heating the water, and the water changed into vapor, the vapor was coming out of the hole of the opening, and along with it, that vapor swept along with it some air. And when the air was swept out, and then I sealed it by putting the rubber stopper on, then I cooled it off in the ice, on the ice tray, then the water condensed, and the pressure inside the can got to be less than the pressure outside the can. So this is happening over here. So what's happening is that the pressure inside the can now is different, but I can't handle it with my hands because it's very, very hot. So I'll take these tongs, I'll pick up the can, and I'm going to flip it over and put it in this beaker. It has water in it, and we'll see what happens. So here we go. You see the can? Got crushed for the same reason we had before, and the can was not very clean. That's why the water is that color. All right. What I'd like to do now is another experiment, but to help me do this experiment, I'd like to call on one of our expert lecture demonstrators, Fred Juergens. So Fred, won't you please come out?
Well, I've got a big, long glass tube here that's filled with a mixture of colorless gases, and there's a little bit of water in there too. You might be able to see some water droplets on the inside of the tube. And the experiment that we're going to do involves finding out whether the gases that are in here will put out a burning match or whether they will allow the match to continue to burn. So what I'm going to do is I'm going to get up here on this step stool, and then I'm going to light the match, and then I'm going to ask that the lights be turned out, and we're going to drop this burning match down into this tube and see what happens. Everybody ready? Yeah. Here we go. Wow. Well, it's very clear that the match has gone out, right? But we had quite a flame in the process, And one of the products of the reaction that went on is the element sulfur. And that's why this yellow coating is on the inside of this tube now. Before it wasn't yellow. Sulfur is a yellow element, and before it was present in a combined form so that you couldn't see its color, but now you can see the color of the element sulfur. So I'm going to take this away and clean it up now because the sulfur really sticks to the glass if you don't clean it out quickly. So we'll see you.
Thank you, Fred.
Yeah.
Let's take a quick look at this last experiment in slow motion. So watch the monitor, and you won't hear the sound again. There's the match that Fred is holding. It's being dropped, and there's that big flame. And you see Fred trying to get out of the way there. Sometimes in my lab, I get very, very big surprises, and I would like to ask you to welcome a very special friend of mine who has been helping out with these programs for many, many years. Is Elizabeth in the audience?
Oh.
Come on up, Elizabeth. Hi.
Hi.
How are you?
Fine. I
Good.
brought you a special token because it's your 25th anniversary.
Oh, how sweet of you and how special of you. This is a very, very nice token. Do you know what metal it's made of?
Copper.
It is made of copper. You're right. And do you suppose we can try to change copper to silver? This is the silver anniversary of the show. Do you suppose we can try to do that?
Sure.
Would you like to try?
Yeah.
Okay. Well, what's the first thing we must do before trying?
Put on our goggles.
Well, I got mine on. So you put yours on. And we're going to do this experiment to try to change copper to silver by putting it in this casserole. That's empty. You see that? Put this in the casserole, put it on top of the burner, and then add a clear and colorless liquid just to cover it up. And after that, what I'm going to do is add a solid, a metallic solid, and we'll have to just to cover it up, and then I'm going to take a match, strike the match after I turn the gas on, strike the match, right? That's the proper way of doing it. And of course, we always strike the match away from us. So there, we'll let it heat for a while. You know, chemical reactions sometimes are very, very fast, and sometimes take a while to happen, and that's why we have to heat them up to make them go faster. So we'll wait for that for a while and see what else we might want to do here.
Okay. Well, I see you have another yellow balloon. Is there anything else you can do with it?
Oh, sure. I can do lots of things with balloons. This is a yellow balloon that has in it the gas helium. And what I'm going to do with this balloon is to add to it something that's left over from the ice cream experiment. What's left over from the ice cream experiment is some liquid nitrogen. So I'm going to put the balloon in this large dish, like so. I can't hold it. I can't let go of it because it'll go up, so I'll just hold it down like this. And then I'm going to add the liquid nitrogen to it, and we'll see what happens. You ready?
Yep.
Okay. Oh, I see some of you are covering your ears. Why are you doing that? Okay, I know why you're doing it, because you've had experience with balloons. So here's the liquid nitrogen, and you see what happens. The balloon, what's happening to the balloon, Elizabeth?
It's shrinking.
You bet it's shrinking. It's shrinking and collapsing because the pressure inside is lower than the pressure outside. We cooled down the helium, and the helium slowed down to the point where it exerts less pressure than it did before. And when the balloon warms up, then it goes all the way to the ceiling. Almost got a hit there, right?
Yep.
I'd like you to walk over to that bicycle wheel that we have at this end of the table. Do you see anything special about it?
There aren't any metal spokes. They've all been replaced with pieces of rubber tubing.
That's right. And what we want to do is learn something about the properties of rubber when rubber gets heated. Behind the wheel, we have a heat lamp, and if you throw the switch on, then you can turn the light on, and we'll see what happens.
This it?
Yeah.
Okay.
The light is on, right?
Yeah.
You see anything happening?
The wheel's starting to turn.
Are you pushing it?
No, I'm not touching it.
Nobody's touching it, right? So the wheel, this is a well-balanced wheel where the metal spokes have been replaced by pieces of rubber tubing. And as the rubber tubing is heated, then makes the wheel turn. So you and I are going to do an experiment to try to understand why that happens. And this experiment we will do with rubber bands. So here's one rubber band for you and one for me. And the way in which we will do this experiment is that we will use our forehead as a way of measuring heat flow in and out of a rubber band. Okay? So hold it up like this, right close to your forehead, and touch your forehead. What does it feel like?
It feels cool.
Okay, now take it forward a little bit, stretch it, and quickly put it on your forehead. What does that feel like?
It feels warm.
Right, so stretching the rubber band gives off heat, right? Now, take it forward, allow it to shrink, and touch your forehead. What does that feel like?
Cool.
It feels cool again, right? So stretching the rubber makes the rubber hot, right? And allowing the rubber to shrink makes it cold. So if we heat rubber, what's going to happen to it?
It's going to shrink.
And that is the explanation that helps us with the bicycle wheel that we have over there. Okay? You learned a few things about rubber you probably didn't know before.
Yeah.
Yeah, but you knew about this part, right?
Yeah.
Right? Yeah, right. Okay, great. Shall we take a look and see what's happening to our experiment over here? Okay, let's do that. And I need to fish it out. It's very, very hot. Let me turn the heat off. Ooh.
Ooh.
I'll have this beaker. Let me just clean it off and cool it down. And there we have a piece of what looks like it is silvery in color, but it really isn't silver. Because the experiment that I did here, I used the copper that you gave me, the copper token. I added some zinc chloride to it and some zinc. And zinc deposited on the copper and gave it this silvery look. So this is not real silver. Okay?
Okay.
All right, but thank you again for the token that you gave me here. It's very, very kind of you. You gave me this.
Does that thing over there have anything to do with your silver anniversary?
That flask, that's silvery? Well, yes, it does. Is there something that you'd like me to do to it or do with it? I'll just set it over here.
Can you pull off the rubber stopper?
You mean just open it up?
Yeah.
I can open it up very easily. Just take the rubber stopper off, as you suggested. That looks like a genie, right?
Yeah. That's neat.
You like that, huh? I'll tell you what was in here. We had some hydrogen peroxide, very strong concentrated hydrogen peroxide, and we had a small tea bag that was held by a very fine thread. And when I took the rubber stopper off, the thread, the bag fell in because the thread wasn't being held again and started this reaction.
Was there tea in the tea bag?
Oh no, it was not a tea bag. It was just like a tea bag. What we had in there was some manganese dioxide. And the manganese dioxide catalyzes the decomposition of the hydrogen peroxide.
Okay.
Well, thank you, Elizabeth, very much. And
You're welcome.
I hope you enjoyed the rest of the show. Thank you very much. And what we're going to do is use this tall beaker and take two liquids out of these two small vials. This beaker has a volume of about 1 liter, and I'm going to mix this first liquid that looks like what? It looks like, yeah, caramel molasses, but it isn't. It's a very poisonous liquid. We should not at all touch it by hand, or even, well, we shouldn't touch it by hand for sure, and we should not put it close to our mouth. Here's another liquid that looked like what? Honey, yeah, or syrup, something like that. And we're going to mix those two liquids together, like so. And I want you to watch very carefully what happens. You know, in chemistry, unless you mix the chemicals, no reaction happens. Sometimes it happens fast, sometimes it takes a while for it to happen. You see there is a very big change taking place here, right? Wait a minute now. This stuff is coming. Wait a minute. No, I did not expect this to happen. No. This is a polymer that we call polyurethane foam, and it's produced by simply mixing those two chemicals together as I have done. I want you to notice, of course you've already seen this, I want you to notice the tremendous change in volume that took place. Something else I want you to notice, when I pick this up and turn around, doesn't fall off. It has become a very rigid substance. Look, we can beat up on it here. See? It's become quite solid. What we should do now is take a look at that beaker that I filled. The beaker had the piece of copper in it before, that I filled with the clear and colorless liquid. And what we're beginning to see here is the outline of a silver-coated tree. That's because the liquid I used was silver nitrate, and the chemical reaction between the silver nitrate and the copper caused the deposition of silver on the copper. You see the solution is developing its own characteristic color. That's because the copper is going into solution. Well, this being the silver anniversary of the program caused me to go back and look to see if I had some notes and some objects from 25 years ago or so, and I did find some. Actually, I found these silver spoons, and they're tarnished. And what I'd like to show you is how we can remove the tarnish. We can remove the tarnish very easily if we use a commercial solution. Here's a tarnished spoon. All we have to do is dip it into the solution. And you see very quickly the tarnish was removed. The tarnish is a compound between silver and sulfur. It's called silver sulfide. And sulfides are in the air. They're in substances like eggs and so on. And they can be removed by using this commercial method of removal, the tarnish removal. I'll cool this off. I'll clean it off a little bit here so it's easy to handle. There's another way to do this, a very simple way. What you need is an aluminum pan. And if you don't have an aluminum pan, you just take any pan and line it up with some aluminum foil. And the next thing that you need is some baking soda. The third thing that you need is some hot boiling water, which I have right here. And I'll get it out. And I will take then some of the sodium carbonate that we have here, bicarbonate, and put it into the boiling water like so. And then take a spoon that needs to be cleaned out, the silver spoon that's tarnished, and add the hot water that has the baking soda in it. So that we cover it. And you see that we can remove the tarnish just as easily because of a chemical reaction taking place between the aluminum and the silver sulfide, and the silver sulfide. All right, now I want to do an experiment right over here with a large flask. I want to empty the water out of this flask. You know, in chemistry, we mix things together, and we see what happens. Sometimes something happens right away. Sometimes it takes a while for something to happen. So here's the first ingredient. Here's the second set of ingredients that I will add to this flask. I'll put the stopper on and start mixing the chemicals together, and we'll see what happens. We already see something happening. The clear and colorless liquids are no longer clear or colorless. And something else is happening, right? I can see myself in this silver mirror. This is the way in which mirrors sometimes are made. And sometimes we make ornaments the same way too, right? And I'd like to show you a very, whoops, here it is, special ornament that I made just prior to your coming into this show. The silver in there is deposited as a thin layer on the inside of the flask. Let's take another look at the tree that we have inside the beaker and see how the white silver now is beginning to deposit. Isn't that pretty? Let me take this box here out of the way. There, you see. It is an interesting display for the chemical reaction between copper and silver. Now let's take a look at this large beaker which has a volume of 4 liters. I want everybody to look at this beaker, because if you look at this beaker and I just told you its volume is 4 liters, you've learned how big 4 liters is. You can't unlearn it. You may forget it, but you can't unlearn it. This is how big 4 liters is. And I have 3.5 liters of water in there, and I have a stirrer. And I'm going to stir the water by turning the motor on. And then I'm going to add a clear and colorless liquid and a clear but slightly colored liquid into the vortex that's developing here. We'll see what happens, if anything happens. What does that look like? It looks like a tornado. You're right. That's why we call this experiment the tornado experiment. Now, what color is this tornado? Should we call this the orange tornado experiment? Okay, let's add more of this. Let's see what happens if we add more. And now it's more like a hurricane, right? And we add more of this. And what happens? More is better? No. Not always, right? But now it disappears. Add a little bit of this. I thought you said it's orange. Well, it starts out being yellow and then turns into, or now it turns into yellow. It was orange, or is it orange or yellow now? See, that's why we do experiments and we make observations about the experiments and try to learn about the behavior of different substances that we have. Okay, what I want to do now is use the same stirrer to do another experiment with another beaker whose volume is 4 liters. You've got that right. It has a stirrer in it. It's empty except for air and the stirrer. And I'm going to mix into this beaker 3 different liquids. Here's the first one. And here's the second one. Anything exciting happened so far? Not really, right? So the volume changed. Well, here's the third one. This is an example of what we call a chemical oscillating reaction. It has in it 8 or 9 different chemicals, including, you're not paying attention to what I'm saying to you. I know how exciting it is to see chemicals in action. Yes, this is called the Briggs-Rauscher reaction. It's named after 2 high school teachers who discovered it in 1973. And it has in it 8 or 9 different chemicals, including water, potassium iodate, sulfuric acid, manganese sulfate, potato starch, hydrogen peroxide, and a few others. And the yellow color that you see, not right now, but when they oscillate, that yellow color that you see right there is the color of what we call iodine, or in the vernacular, iodine. And then it combines with the potato starch to form this deep blue color that's almost black. And these oscillations continue for a period of time. And this is what makes science fascinating and interesting and also challenging in terms of trying to understand what it is that is going on in a reaction of that type. Now, what I would like to see and check out on to see is if the ice cream is ready. Is the
Yeah, it's ready.
ice cream is ready?
Bring it in right now.
Okay.
Here we are. Here's the ice cream.
Oh, thank you.
And
you've got
here's
some bowls and
there's some bowls
Yeah,
and
yeah.
some other things.
let
So
me
let's-
set these.
Yeah, let's put those right.
What's this that you've got here? That's another interesting and colorful set of beakers.
Well, yeah, I was putting together some beakers to make some of the chemicals, and I was stirring it around, and I noticed that when I was stirring it, I heard sort of a tone, and so I started messing around with beakers and just putting different amounts of water in them to see if I could make anything that sounded interesting rather than just explosions and all that kind of stuff, you know. So here's what I set up, and I'd like you to listen very carefully and see if you can tell what's going on here. This is for Bucky and for the Hall of Fame Bowl, right? Okay, let's hear it for Bucky. Great.
Thank you very much, Fred. And of course the ice cream is ready, and here it is. And let's take some out and put it in this bowl. And I would like the person to try it for the first time to be Elizabeth, so I'll bring it over to Elizabeth. See if Elizabeth is willing to try it. Are you willing to try it?
Yeah.
All right, here you go. What does it taste like?
It's good.
It's good. What flavor is it?
Strawberry.
Of course, it's strawberry. Thank you, Elizabeth. Enjoy the rest of it.
Okay.
What I'd like to do now is a reaction in this special apparatus that consists of a glass spiral connected to a large glass funnel, and down at the bottom is a large glass flask. And I'm going to use a clear and colorless liquid and mix it with a clear and colored liquid. But I'm going to do this mixing in the dark. So here we go with the lights off. I'm going to mix those. There we go. This is an example, with the lights up please. This is an example of what we call a chemiluminescent reaction. Chemiluminescence is the phenomenon whereby energy is released in the form of light but not in the form of heat. What I would like to do is really express my great appreciation for your sharing with me the excitement of this very special silver anniversary show. You've been a very good audience, and I'm very, very thankful for...
Excuse me, Professor Shakhashiri.
Yes, Janice?
Fred and I over in the lab have put together just one more little tribute to your anniversary, and I wonder if you have an extra minute.
Of course we have time for that.
Thank you.
This is Janice Parker, our second expert lecture demonstrator.
Can I have someone turn the lights down, please?
Thank you, Janice. Thank you, Fred. That's very special. That really is.
Happy
Thank you very much. 25 wonderful years. I want to thank you all and urge you to do science and other things that are worthwhile in life. But don't forget, no matter what you do, science is fun. Thank you very much. Thank you very much.